So I am glad to invite Tsahi Shemer to share the car company's perspective on sensing and expectations from the Academy. Tsahi Shemer is a Senior Director of R&D programs at Elbit Systems and the Chairman of the Avatar Consortium. So please, Tsahi, the stage is yours.
Okay, thanks. Hi. So I'm Tsahi Shemer, as mentioned, and I'm the chairman of. Is that better? Oh, okay. And I'm the chairman of Avatar Consortium. A few words you saw earlier in the previous panel. Some of the participants, and we're an Israeli consortium. Sponsored and funded by the Israeli Innovation Authority. And we're a group of companies and research groups from the academia. We perform research and development in several areas that we defined when we established the consortium. We deal mainly with data fusion, multimodal data fusion, with perception, scene understanding, navigation, and so on. And we are doing it by extensive collaboration between, among the companies, and mainly between the companies and our research groups. And so we have very good experience with that. Helps us a lot to achieve our goals, to stay at the front end, and to have good results. We heard earlier, and we are all familiar with the fact, it's difficult, that in order to have autonomous driving, we must have a lot of data. In order to do that, we have to use all kinds of sensors, and as we said earlier, sensor suits and actually sensing strategy. Each OEM has its own. Each sensing strategy brings or has pros and cons, and of course brings challenges that we want to address. So in this session, we will hear from three managers of three leading OEMs, Ford, GM, Daimler, and they will share with us their view and their thoughts of what is their sensing strategy, what are the goals and challenges it brings with it, and how they see collaboration with academy and research, and academy research can bring AV to be commercial, and I believe we all want it to happen as soon as possible. So the first, I invite Mr. Asaf Kagan, VP R&D at SAIPS. Asaf, please.
Hello, everybody. My name is Asaf Kagan, and I'll be speaking today about several aspects of sensing technologies for autonomous vehicles. But first, let me quickly introduce myself. I started with a double degree in physics and electrical engineering, and continue to lead several projects and teams in work related to signal processing and communications in the Army. But after my second degree in electrical engineering, I started focusing more on computer vision and quickly adopted the revolution of deep learning to provide algorithmic solutions for various problems. I brought my experience from small startups and large corporations to SAIPS, which is a wholly owned subsidiary of Ford. And I started there as an algorithm developer, and I'm now leading the entire R&D work of the research and development teams. There are different levels, and in fact there's a wide spectrum. And it's customary to divide this wide spectrum into 6 discrete levels. In the first 3, the human is responsible for driving, and the vehicle is just assisting. And in the next 3, the vehicle becomes responsible for the act of driving, and the person is just there for the ride. If there's an emergency or something, the vehicle needs to be able to pull over by itself or stop or hand over control to the person, but the responsibility is on the vehicle. So I can go into some of the details here, but as you can see here, the level of autonomy increases as the level increases here. We start from simple warnings and momentary assistance, like emergency braking, and this goes up and up in levels of autonomy into full autonomous driving without any limitations whatsoever. So as the levels of autonomy increases, so does the required sensing complexity and accuracy. So for higher levels of autonomy, I need very accurate and very sophisticated sensors and sensing capabilities. And of course, perception capabilities built on top of that. And this goes hand in hand with the business concept behind what goes into autonomous vehicles. If I look at higher levels of autonomy where the vehicle is responsible for driving, like the case of robo-taxis, there I can afford to have very expensive and elaborate sensors because the business case of a robo-taxi is something that's worthwhile investing, even if it's relatively expensive. LiDAR sensors and radar sensors. And this might tie in to some of the things you heard maybe in the previous sessions. Each of them has their own pros and cons, and I'll go into it in the next slides. Each vehicle may also be equipped with several of these sensors. Several sensors from each type and several sensors from different types as well. For example, I can have several cameras covering a 360-degree view of the scene. And I can have a combination of cameras, LiDARs, radars, and so on. And of course, each sensor can have different properties. I can have short-range sensors, long-range sensors. And of course, there are different sensors as well. You have ultrasonic sensors, which are mostly used for very short range maneuvering, like parking assistance, and other sensor types as well, but these are the most common ones. So as I said before, each of these sensors has their own pros and cons. Cameras are by far the most common sensor on a vehicle, on an AV. They are cheap, relatively cheap. They are high resolution. They have relatively long range view, depending on line of sight. They have color information, but they are very sensitive to lighting conditions, weather conditions, and they don't provide 3D information. If I want 3D information, for example, I have radar sensors, which are much less sensitive also to weather conditions and lighting conditions, but they lack color information, they lack resolution, and generally the accuracy drops as range increases. Of course, today technology keeps advancing and there are better and better sensors out there, but these are the main characteristics of these sensors. If I want very accurate 3D information, then I have to use LiDAR sensors. LiDAR sensors are by far the most accurate 3D sensors. They are accurate to very high ranges. They are also not very sensitive to light conditions, but they are sensitive to weather conditions. They don't provide color information, and they are very, very, very expensive. So each of these sensor types has their own pros and cons, and we firmly believe in sensor fusion. Since AVs present such a tough problem to solve, we need every bit of orthogonal data source we can find. And as mentioned here before, the way to do this is with sensor fusion. By combining different sensor types, we are able to use the strengths of different sensors to mitigate the limitations of the other sensors. And there are several buzzwords out there. For example, you have early fusion, which means taking into consideration all the raw data from the different sensors and process it jointly. This usually requires very accurate synchronization between the different sensors. But you also have late fusion approaches as well, where each sensor is processed separately, and only at the end the results are aggregated and combined. So there are different approaches for sensor fusion as well, and this is an active field of research. Here we can see an example of sensor fusion. So here, for example, we can see a raw LiDAR sensor output, which is a 3D point cloud. But when we add color information, the scene becomes much clearer, and we can make out all the different objects in the scene and understand what's going on. We can use this to perform different operations like semantic segmentation, for example, which means classifying each point in the point cloud into one of a predetermined set of object types. For example, we have here sidewalk, road, vegetation, pedestrians, building, and so on. And this is just a rough example of what we can do with sensor fusion, just to illustrate the strength of combining data from multiple sources, multiple orthogonal sources. So, driven by these limitations, the industry and academia strive to continue ability to create large amounts of data is crucial. And how do we do it? There's basically two approaches to creating vast amounts of data. One is simulation, trying to simulate sensor data as accurately as possible with all the sensor artifacts, and this is a pretty tough task. Even today, the most top-notch simulation tools are able to provide very high-quality images, for example, but you can almost always tell it's not really a real image. There are very large advancements in the field, and we hope to get there soon, but still it's an open challenge how to create, for example, for camera images, how to create photorealistic images that can even confuse a human if they're real or not. The other way is to do fleet collection. If we have a large fleet of vehicles equipped with sensors driving in the field, we can just record this data and we instantly get access to huge amounts of data, so-called collected in the wild, which is able to provide us with interesting edge cases that we couldn't think about by ourselves just by driving simulations. And I want to conclude with one more note. So we saw what we need for sensing, and we saw what we need for data collection, and all of this is great to do accurate perception. But perception is just one building block of building an AV. Perception is not enough. We need other building blocks as well, like mapping and localization, and more specifically planning. And while the industry has a lot of work going into mapping and perception and localization, the field of planning is pretty immature compared to the other ones. And we consider this the main challenge today in creating an AV. The work on mapping and perception and sensing and localization and so on is making great strides. There are a lot of people involved working on it, and the rate of advancement is very high. We are confident that this is going in the right direction. But the field of planning remains an open issue. For example, here on the right, you can see an example of a vehicle trying to navigate a very narrow stretch of road. And you can see there are cars parked at both sides, and you can see there are vehicles coming from the other direction, and the vehicle needs to decide what it's going to do. Is it going to yield to the other vehicle coming from the other direction? when it sees the other vehicle stopping, does it realize it's yielding to us? Or is it just stopping momentarily? Do we now begin to drive? All these negotiations and decision making, making it reliable and working in large scale with as little errors as possible is extremely challenging. And we believe this is the next active field that the industry and academia should be concentrating on. Thank you very much.
Okay, thanks, Asaf. Questions? Audience?
Yes.
That's a small note. There are simulations which are fully photorealistic with improved performance using Fourier systems.
Okay. Yeah, I'm familiar with.
Cognata, I should protect.
Yeah, I'm familiar with Cognata and works performed by other companies in the field. And as I said, this field is making great strides and great progress, and we are confident it's going in the right direction. Even if there are some limitations yet available, we are confident in the near future they will be resolved.
Thank you very much.
Yeah. Yeah. Correct. Fleet collection does not solve our labeling problem, but even getting raw data sometimes is challenging. I mean, with simulations, we can get very large amounts of data. We can also try about thinking how to simulate edge cases, which are pretty rare and hard to collect. But some edge cases are just unexpected, and we can never predict them all. This is something that usually only comes with very, very large-scale collection in the wild of real data. Just things we can't expect with simulation. So the only way to do it is collect large amounts of data in the wild and label it.
Okay, anyone else? Okay, so
Okay.
Asaf,
Thank
thanks
you.
a lot. Very interesting. Yeah. Now for our next speaker, Mr. Gonen Barkan, which is a radar development lead at General Motors. Please.
Hi everyone, I'm Gonen Barkan. I'm leading the radar development in General Motors globally. Global team, and maybe we'll do a quick and first I want to thank Asaf for taking a lot of my work from me, so thank you. It's very helpful. Let's see if it works. Okay, so just quick introduction of the team. So it's a global team both in Herzliya and in Warren, Michigan. And we're responsible for all the radar development in General Motors. And all kinds of unique technologies from antennas up to how the paints behave on the vehicles. So, I thank Asaf because it's really, I think it's a great segue to what I'm going to say because I assume most of you are already familiar with it. And I want to give you some, how do we see this, this domain. So when you go to choose a sensing suite for a vehicle, so we look at the 5 major elements. So radars, with all the benefits that were mentioned, so I think are suffering from the, in one hand, being cheap, etc., but still, there's the gap of performance that needs to be addressed. Big problem with ML pipelines and simulation capabilities in radar. Those radars do not exist yet, so the database do not exist, so nobody develops the pipelines. So there's a big gap there. Everything calls it noisy, right? So it's not robust enough. It's a different modality, of course. And there's no modeling technique, effective modeling technique like photorealistic for radar. And not just this, there's not a lot of drive in this industry. There's no other industry that is pushing this technology, in camera, for example. And it's considered to be very mature. It's governed by the tier 1s. And usually OEMs doesn't have a lot of skill set in this domain, which causes the chicken and the egg problem of getting the innovation. So I call it the 30 dB gap. Again, of course, it's not just dBs, of course, as you all know. But believe me, bring me the 30 dB, we'll be in a much better shape. So I think this is, I think, where the academia, the OEMs, and the tier 2s and the startups need to work together to bring the radar to where it should be. And definitely there's work on the LiDAR stuff, but it's happening already. So I think I think it's in the right direction. So I try to put the big players on the board, and where do I see the synergies here? So let's start with the startups. So by the way, a lot of good startups in the industry, and we're trying to be on top of everyone. So if we missed anyone, let me know. So I think the right way is to focus on practical innovation, find the pain points and make sure you can address them in your solution, not just and I think it was mentioned back by Innoviz, like not just cool tech, make sure you solve practical problems and not very narrow technology solutions, because that will allow us to pull it in. From the academia, I think that the academia is in a very unique situation where it can tackle the hardest problem. If I have some time, I'll maybe flash it around. Because it's not under the axe of the funding or under the axe of the return on investment or the execution. And it can explore the more challenging areas that lies ahead, which the other companies here find it very hard. And if they do this, if the academic is doing it and not the very narrow academic, so I can publish a paper, right? Or have a very cool instrumented bench, I think that will allow us to collaborate much better. For the tier 1s and tier 2s, I call it incubate innovation. They should be the hub to incubate the innovation. They have the right mindset, and I think that's also mentioned on what is productionizable, how to do it, what makes sense, and they need to be the natural candidates to pull this innovation in. So if the tier 1s are focused on amortizing what they already have, or just doing incremental changes, and the tier 2s just follow what the tier 1 does, that will keep the stagnation in this field. And this is where I think our role in the industry is, and we're actively doing this for the last 2 years. So our role is to accelerate and impact everything here and create a win-win situation for everyone. So we cannot just sit back and be passive buyers. We have to be active and create a synergy. So that's what I had, and feel free to look on some of the hardest things we expect to be solved. That's it. Thank you very much.
Okay, thanks. Maybe we have some questions from the audience. So just a short second.
Yep.
Questions? They are mainly taking pictures.
Yeah.
Hi, thanks. One question to the 200 gigahertz. Where do you see the application, and where do you get the power to really cover the vicinity of a car with 200 gigahertz of frequency of operation?
Yeah, that's so as the radar guys, I think everybody mentioned the resolution challenge, right? And one of the ways is to increase the frequency. And we know there is regulatory problems, and I think one of the areas we want to explore is where and maybe do a consortium of OEMs and figure out what's the right band that we can use and leverage for these type of applications. But we have a big roadblock on the silicon level that we have to push the tier 2s to get there. And I think the first stage will be to figure out what is the band that we need to work together the OEMs and the tier 1s to figure it out.
What about output power of your device at 200 gigahertz? I think you have the atmospheric attenuation, you have the bumper and all this stuff, and how do you get the circuits that provide really the output power that you can achieve the distances that you need?
Yeah, so great question. So the 200 giga is not the accurate frequency. We're looking for a dip in this, and we think that probably that will be mostly effective for the mid and short range and ultra short range applications. and not so much for the extreme long ranges. But I think for this to get into production vehicles, we'll need to have very aggressive industry push to get there. That's it. More questions?
Okay.
Okay,
Thanks a lot. Gonen, thank you very much. Very interesting. Thank you. Okay, so last speaker for this session will be Dr. Jürgen Dickmann. He is head of radar and radar perception at Mercedes-Benz. Please, you're welcome.
Yeah, thank you for. Does it work? Ah, yeah. Okay. So thank you for being here. Just 2 words to my person or my background. I started as research and advanced development and ended up now as completely responsible for research, advanced development, and serial development. So I really understand all the problems that you are talking about, yeah, and probably much more, because I have everyday problems in getting the serial stuff done, and that is far away from research. Yeah, so that is a very, I think, therefore, the entire talk is very similar to yours and the speaker before, but it's probably hopeful some information with reference to serial and everyday life. So last time I was here, I also explained this Bertha drive for those who have heard this. I think it's really long back. 2013, we got the task from our managers to say, okay, you as a car OEM of luxury cars, you have to look that the shape of the cars is still looking like an icon-like luxury car, and look for the appropriate technology that fits and allows as much L5 as possible. That was the task at this time. And it was also a nice time when Mobileye said, okay, I have vision with neural networks, and we said, okay, we can do everything with stereo vision. And at this time, the managers decided, just put it vision only. And the good information to all the radar guys here is, this took roughly half a year, not much more, longer than that. And with every day the project lasts, we increased more and more and more radars into the car. And I think this experience is similar to that what I observed since then. If you look in the internet to see how all these startup companies and smaller groups started, they start always with the typical university setup, vision and LiDAR. And if they face to reality and all the everyday problems and really to make a product that you can release to a private owned user, they increase more and more radar. For all the radar guys, it's not a surprise. For all the others, I say, look, since the invention of radar, in how many industry sectors radar is introduced, not only defense, Earth observation, many other areas. And there, radar is still there and has improved dramatically. There has never ended any kind of development phase, and that it makes radar so attractive. It works when all the other sensors fail. I think that is a very important issue. And if you really do the survey, I spent some time on the internet to see how Cruise and all the other groups started, especially the universe-like ones, they end up with increasing radar. And even if you look on Waymo, as they started with Google, as Google stuff, they had tremendous amount of LiDARs, and now they have improved the radar stuff, have improved the radar itself, just as an idea. I think this video is nothing new, much better now today, but just to give you an idea what we achieved 2013. And this was under the prerequisite, don't change the form and the shape of the car. I think I can try to skip this here. Yeah, let's go back here. And then we had a sub-following project with Bosch, where we said, okay, let's look on all these use cases which we could not solve at this time with the methods and the technologies that was available 2013. And the decision was, don't look on the vehicle, how it appears, just put the sensors in that you think that you need, as much as you need, and then you can see what is the end of this project. And then you can ask yourself, if this is a car that I would like to buy as a luxury car, as a private owner, and then add on all these change of cloth that the pre-speaker said. costs, and all this stuff. And then you really come to a point, oh, I have to really revise my sensor setup, and I'll come to that later. But even in this status, we had to face, for a private-owned car, and not a robotaxi, we have a long way to go to come really to an L4 or L5 system that we can really hand over to everybody user. And therefore, I think it's not as the internet says in 2013, tomorrow you can buy L5 cars at the dealers. There is some way to go. And the reason is not really performance-wise. It's more the legal stuff that you have to fulfill as a car manufacturer, because you take the total product reliability, the legal responsibility that your car can be really handed over to a private owner. So what is happening in the meantime? So that is what we do. Develop, not in research projects, do it real life with the real customers, and improve day by day the performance, learn what is possible and what not, and from next generation to next generation, we increase the performance level of the cars. And in our S-Class, which has been launched last year, we also introduced L3 highway functions. But that's the other part of the business. We are not allowed to release the software. We are just waiting with the software already equipped in the cars to drive this. Even in Germany, there's no allowance at the moment. So that is the next step towards L4, L5 driving. We need the regulation to drive these functions today, and then we can really improve also to a higher automation levels. Then also one add-on to that, what the speakers before told to us is what drives the performance and hence the cost of the sensor setup. And in the past, my talks were mainly dealing about performance issues. But since I'm now a serial development guy, I really have to face every day a huge amount of requests from safety, product reliability issues, and really security. And security because it takes a huge amount of your computation power in the sensor itself. And that drives cost. So for all the people who are trying to develop the next generation of sensors, please take into account that safety, product reliability, and security algorithm have to be implemented and have to fill the requirements of the OEM. And I'm sure that OEM has a different other kind of security approach than we have. So be aware that this drives cost. Another thing, what is our OEM role? I think we, probably also the four speakers said the same, have to take care on what is the sensor setup. Not only performance-wise, it is also cost-driven. And here it's really the same keyword as you said from General Motors. We have to take care on what is the number of devices, what kind of devices, at which place of the car, so that we can afford to have this payable, affordable for the private owner. And because that's a totally different game compared to robotaxis. And here, I'm really happy that all these spider diagrams that I used 20 years ago when we did our first driver assistance systems are now coming up once more again. And unfortunately, you can't really see the color code, but I think here, this is green one, this is green one here, and it represents a radar, and the blue one is always the opposite sensor type. And the good thing of these spider diagrams is that it really, that just really shows you where the differentiation or the common performance scope of these sensors and where they can work complementary or they help each other. And in the past, and even today, we always discuss about LiDARs, and the most motivation for LiDARs is resolution. But all these spider diagrams in the past ignores the tremendous improvement that radar can do. And I also refer to Mobileye. Puzzle piece here. They say, okay, even in the near future, they have radars available that can do much more performance than what we have today. And they, as one KPI, say, claim to have a 10 times larger amount of virtual channels that you can play with. That is not really compatible or one-to-one translation into higher resolution, but it allows everyday capability. And that is also a big point. And if you then play in these games and look what you can do to get better resolution, then the question really comes up, what do you need a LiDAR for? And the only answer that I have at present is legal requirements. That you say, okay, if I go to L4, L5 systems, I have to really fulfill all this legal stuff, decomposition of ASIL levels, product reliability issues. And then the question is really, do you need the third technology? And today I would say yes, because we are not here at this level where the radar could be. But in the future, if you have a vision system that you see Mobileye is driving, many other companies are driving vision only, you need a redundancy sensor that also helps you in situations where the vision can't. Then you have this. And the question is really, when is radar really capable of providing all this resolution stuff that is needed for L4 and L5? And I really encourage you to work in this direction to enhance the resolution of the sensor. Very old idea. When I was also responsible for fusion, I also had the chance to work with very, very young colleagues. And even at these days, the answer to all the question was DNN. Do everything with artificial intelligence, deep neural networks, CNN stuff. And then I asked them also, how do you use the radar in your fusion stuff? Mainly they said, okay, it's just for ranging, a little bit of velocity, and that's it. And then I said, okay, that cannot be really the end of the story. You have to do really much more. And I came out of the defense industry and I recognize what the people could do there. And if we translate many of these knowledges to automotive industry, then I think you make a jump in performance. And that is, I would also like to encourage you, take many of these approaches that were able there. And since then, after Bertha, I took many chances to talk with tier 1s, tier 2s, especially tier 2s. They have to push the tier 1s because the tier 1 starts to work if you pay him. He is very reluctant to do things, to spend costs without getting an assurance that he has return of investment. So the innovation has to come from tier 2s that say, here, tier 1, I have a very good idea. From startups, for example, I have a very good idea that can solve problems. And if you then discuss with the OEM, as a common team, we can really make the push, the next step. And that is, I would also say, as a lessons learned. The OEM has not only to discuss with tier 1s, go to the tier 2s, tier 3s, go to the startups, look where the new ideas are, and then convince the tier 1s to make the next step. One innovation at this time, I had to work with a radar that was state of the art, but has a rotating role to do the beam steering, beam sweeping. So it was fixed, not scalable to functions and so on. So I think the first thing, and I think many companies or startups going in this direction, is digital and try to do as much software defined as possible so that you are flexible and so that we can come away from this point. I have some use cases, and for that I need any kind of sensor type. What we need is a sensor type that can be used from L1 to L5, and for a S-class, a van, a truck, and the smart. And for all these, it has to fit, because we cannot afford many, many different kind of technologies. That drives us crazy and runs up bankrupt. Another point that we also take care of is on get resolution as much as possible. And that means not only spatial resolution in azimuth and elevation, it also means in time, and time represented by Doppler and micro Doppler. And if you play with all these puzzle pieces together, then you have many degrees of freedom how to make your radar design and your radar architecture. And the background behind that is to get as much pixels, radar pixels per object in the environment, and then you can really adopt to the environment ecosystem that has been already implemented by vision guys. And if you do it intelligent, you can really adopt to this. Although the radar data stream is totally different to that of a vision thing. And I give you some ideas how this could work. But learn from others. That is also a big thing that accelerates you. And I'm happy now to see early this year that the very successful company that is very fast and innovative took the same ideas more or less in parallel. So it could not be very wrong. The swarm doesn't fail. Yeah, and I think the colleague from General Motors said something similar. So that is the way we have to go. Another thing, real life, in the past, I did not really pay so much attention on how to make a package, a vehicle integration as a serial car. But that drives me crazy every day. I have every day with the designers and the construction guys in our cars, in our present serial projects, fights in millimeter range, not centimeters or meters, millimeters. Because not only in combustion engines, even in E-driven cars, the space is occupied. Everywhere where you go to the car to place any kind of sensor, they say, okay, there's NCAP, low speed crash, pedestrian crash, all these legal requirements, and you have to face on millimeters. And if you then grow the sensor as it should be, it becomes larger, and then it becomes really dramatic to find a place. So just to scale the sensor to come to this resolution comes to an asymptotic limit. And therefore, and that is a point I would like to give you a mind teaser, look for alternative approaches in addition to just proceeding the normal line that you do. In terms of what also is done in the military area quite often, use this radar and this radar, combine them on a central ECU by calculating an artificial aperture. And then you have standard radars that can work as high performance radars just by doing software and doing some manipulation in the sensor itself, clear. But this is, I would rather like to encourage you, and if you have ideas, and please approach me, I would be really eager to discuss it with you. Because that is my feeling, that is the way we have to go in the future. Not becoming bigger, put more intelligence into the vehicle so that we can cope cost and get and gain more performance. And another point with packaging, we take tremendous cost, or would take tremendous cost if we implement many LiDARs in the car. Stone chip protection, cleaning, you have to provide line of sight. And this, you see always, a car doesn't look like a nice icon-like shape design. They look artificial. And ask yourself, if you're not entering and hiring any kind of robo-taxi, if you would go to a private-owned car, would you really buy a car that looks like the cars today, which having all these LiDARs on top? I leave this question to you. One rough idea about the data. The industry standard is on radar side was objects level so far. But that didn't allow you to go with machine learning, neural network stuff, artificial intelligence. You have to handle and deal the radar like a camera system. Provide raw data, some kind of raw data that is manipulated a little bit intelligent so that they can really be considered as radar pixels. And then the entire mathematical world can be used for that. I speed up a little bit. Then another lessons learned out of the time when I was heading the fusion guys, if you don't let the radar stay with detection and ranging, you are lost. The fusion guys have a much simpler game to play if you put a lot of clean data and improved data to the perception system. And that means look on how you can provide the static environment, not only to plausibilize mobile ghost objects and all the things from the dynamic stuff, get yaw rate and motion data summarized, ego motion estimation for localization, because localization is the key, especially if you would like to be insensitive against spring, summer, and whatever kind of variation. Radar just looks on persistent structures. And that also helps to find landmarks in terms of poles, lines, characteristic radar regions to make your system extremely robust. I can skip this here just for sake of further transparencies. And that is one idea that we took to apply the neural network stuff, has been developed by our vision guys to radar. And we looked on the occupancy grid stuff and implemented a radar-based stuff with many radar-specific layers. And then said, okay, this grid looks very similar to an image. Apply CNN stuff. And then we did a really fast jump to really annotate static information out of the radar. And that's also a key issue. What we are struggling a bit more is dynamic stuff. But just to give you an idea, and I like this image because adverse weather condition in Germany, we have a lot of fog, a lot of snow, ice, and everything like that. And how you can handle this with optical sensors. I think there the radar has a huge, big of improvement. And the data is also cleaned up so that you have really all these dirty information out of the map. We are struggling a little bit with the dynamic stuff. I do not know how to start this video. Okay, let's do it without. I think to really put on each point an annotation is very difficult because you have so many reflections from the radar. But if you can do this, for all the guys who are doing clustering and object formation algorithms, they will love you if you can put annotation to each point, because clustering is then done by the neural network itself. If you really know this is a point that helps you to make a box fit to this car, that you can really see, okay, length, dimension, the emotional state of the stuff, that helps you tremendously in getting near bypasses, pre-crash scenarios, and something like that. And as a last slide, I think the rest is fine. I would also like to invite you to go on our RadarSense webpage, where we have radar data available, where you can help us improve all this classification stuff based on radar. Thank you.